Hola a todos, bienvenidos y bienvenidas. Bueno, esperemos que os esté gustando mucho TechFest, que hayáis visto muchas charlas hasta ahora. Y nada, aquí en Track 4, pues nada, os dejo con Dan Casas, que os va a dar una charla sobre 3D Digital Avatars with Machine Learning. Un aplauso.
Gracias. I think the talk is going to be in English, just to inform everybody. When I submit the talk, I just said in English, so it's supposed to be in English. I guess mostly Spanish speakers, but we'll skip to the original plan, okay? So today we're going to be talking about 3D digital avatars and how machine learning is helping us in building those. And basically the talk is about a summary of the state of the art in terms of research, academic research, on what are we doing in building digital avatars. It's a mixture of works that we did in our lab and works by other labs. I'll try to emphasize which works are done by our lab and which works belong to others. All right, so to motivate a little bit the talk, when we talk about virtual humans, I guess everybody would have in your mind, you would have an image like this, right? So what you see here are 3D scans, so these are static images, but they are 3D, so they are actually renders, they are not images, right? So in here we have like very natural looking images where we have different humans wearing different sorts of garments. Each garment deforms with naturally, some wrinkles appear, different face expressions, even different body expressions. So, so those are like static scenes that are rendered, and they look quite natural, right? So our goal here is how can we use AI and machine learning in particular to get this kind of scenarios, and ideally where the avatars move, and basically how we can recreate the realistic world in a digital manner. Oops. All right, so that's kind of the goal of what perhaps we have in mind when we think about the metaverse and all this stuff that is quite popular these days. So we're going to see a set of techniques that we can use to create these kind of scenarios, and ideally interactive scenarios. All right, so to get virtual humans, I think you can split the work you need to do in 3 different blocks, and I'll try to introduce different techniques for each block. So first we need to model the underlying human body in a kind of undressed or naked way, like how really we are. Then we need to model a little bit the clothing we're wearing and how the clothes deforms. And then we also need to model a little bit the appearance that we have. So like if we have this set, we can more or less already model humans. So basically along the talk, I will give some hints or some techniques that can help us in each of these blocks. All right, so to get started, let's see how we can model humans. This section is mostly about works that other labs have done. So just to get you familiarized with the kind of algorithms and techniques that we'll be using, underlying any digital human, there is always some sort of approximated human or coarse approximation of the humans. So this is usually called what is called a parametric human model, and actually the most popular in academic research, but still also in industries, is one that is called SMPL body model. So if you think about that, this is basically when you play a video game and you have a set of sliders that you can tune your avatar, right? So basically, here's the same idea. So we have a set of sliders, and with these sliders, we can manipulate the shape of the human, right? So roughly speaking, only using these 10 parameters, so like 10 numbers, we can model any body shape as a human body shape, right? So basically, any model that we will use along the talk, and underneath, it has 10 numbers. Like everybody who's sitting here, your shape is approximated with 10 numbers. It's a coarse approximation, but it's usually a good approximation, right? So we have 10 magic numbers that kind of represent your body. Now we will see how we can get those. So basically, sorry for the math here, but just to have a little bit of formalism here, we're going to call this 3D mesh an M. So M is a mesh, like a set of vertices and faces. And then these beta and theta are two sets of parameters that are basically numbers that encode your body shape and your body pose. So beta is like 10 numbers, okay, just 10 numbers. Those 10 numbers, which are the values of these sliders, they control how is your body shape. And then this theta parameter, this theta parameter is the pose. To understand what I mean by pose is basically the articulation of your body. So in this other example, you can see an interactive visualization of this body. So now we're manipulating the body shape. And then when I tweak the body parameter, I'm basically manipulating the articulation of my body. Okay, so this is like the more coarser approximation of a virtual human, but of course it doesn't look like as we look, right? But this is like the underlying model that every AI machine learning application uses to approximate humans. And then what we're going to be doing is we're going to put stuff on top of this. Okay, these are quite powerful tool because it's super simple, but it gives us a good starting point for any human, right? So the cool thing here is that this body model was actually built from many real models. So the people who introduced this basically used 4,000 scans of real people. And then using these 4,000 scans and a little bit of statistics and math, you can build a statistical body model that represents these 4,000 scans. And then with these 4,000 scans, you end up having this model that only uses 10 numbers to represent all of those, right? So then is a way to approximate a kind of a basis of the human. This is actually very, very used in academia. Actually, everything I'm talking is actually open and free. So if you Google this, you will find free implementations and open source implementations of this stuff. Okay, so now we know more or less how we can approximate humans, right? So now one question that you might have is like, okay, if I have an image of ourselves or somebody else, how do I, find the parameters of this human, right? Because then if we want to, I don't know, do some virtual try-on and try virtual shop, we need to get our own virtual human, right? If we want to play a video game where our character is the main character, we need those parameters. So basically, one question that one can answer is, that is willing to find an answer is, given an image, could be it could be even a selfie that you do with your cell phone. How do I find my beta and theta parameters, right? So how do I find the 10 values that represent this image, right? Okay, so the cool part here is that machine learning is helping a lot here, right? So in the previous slide, using statistics, I built a model of humans. And now with machine learning, I'm going to show you how we can actually find the beta and theta for any human, for any image. That's what we do, right? Because it's important to understand that in the previous slide, we only built the model. And now we want to find the parameters of the model for ourselves, right? So machine learning actually helps a lot here. So I have a super quick summary. Of course, there's a lot going on here under the hood, but just for you to understand what is the high-level details that are going on here. So given an image, nowadays what is quite popular is you use a neural network to encode this image, right? And then basically what you're going to have here is that this image is basically a matrix of pixels, so a lot of numbers. And using this encoding, you kind of find some like the relevant information in here. It's pure statistics as well. So don't worry about this, but it's basically a small representation of this image in a vector. I think this is the most complicated slide of the talk, so don't worry if you get a bit lost here. Then after we get this encoding, we get some low-level representation of here. Here you can have maybe 100 numbers that encode this image. And then you train one of these neural networks that is called regressor, that given this information, that is kind of a compressed information of the image, it will output the pose and the shape, the beta and the theta that I was talking in the previous slide, okay? Usually you also output the camera position, because of course this human can be captured for any image, for any viewpoint, right? So these models basically would output pose, shape, and the camera position where this image was taken. Right? Camera position is important because you look bigger when the camera is closer. Okay, so whoever is a little bit familiar with machine learning knows that this is super cool, but the problem here is that we need to train this model, right? We need to find what is this encoder. We need to find the parameters or the underlying parameterization, right? So in machine learning, we'll talk about supervision, right? We need data to train this model. Now, the problem is we don't have we assume that we don't have the ground truth data of this image. We don't have like the 3D pose of all the images, right? So we need to find a trick to train this model. So the trick here is that once we get this output, we can generate the mesh, like the 3D human, and from the mesh we can actually kind of paint the 2D body joint location. So these points here that you see in green, I don't know where my pointer is. So these points here in green are like in the joint positions in the camera space. Okay, so there are 2D points. So the cool trick here is that in order to train this network, what we're going to do is we're going to say that I want the green points to be close to the red points of the original image, right? So when this network gives me green points that are located similar to where the red points are, I know that the shape and pose parameters that I'm getting here represent the human, right? So again, this is a little bit low level, right? But what is important to understand here is that I'm getting pose and shape, which is 3D information, but only using 2D supervision, right? Because the only supervision that my neural network is minimizing are these points that are points in camera space, right? So in here, we're showing how you can train a neural network, and as a ground truth data, you only need that somebody clicks in this image for many images, but you don't need 3D, which is super expensive to get. Okay, so basically this was just a quick summary how we can use machine learning to infer body properties from images. There's probably 1,000 different methods that do the same thing, but the high level is this one, right? So just in case you got bored in the previous slide, here you have some very cool results of what you can get with these methods, right? So given a single image as an input, actually, this works roughly at 10 frames per second. So given an image as input, you get the pose and shape parameters of this human, right? So this works, as I said again, 10 times per second, right? So in our modern GPUs. So we can already do quite a lot of works, right? So we can estimate the shape and the pose of humans from video input almost in real time, right? So this is quite powerful to find like the parameterization of any human, right? Like an obvious use case here would be you want to go online, buy some T-shirt, and you want to know if your T-shirt fits you or not, and then you need your the parameters of your model. No? So ideally, you can generate the parameters of your body model, and then the computer knows how your body is, and then it can approximate how a T-shirt would fit, for example. Right? This is what I'm going to be talking next. So this is basically the first step, right? So the talk is digital humans with AI. So here the first step is, okay, using computer vision and machine learning, we can find an approximation of our surface, right? But there's a lot more we have to do, right, to get virtual humans. So with what they show so far, we have something like this, right? Which is not yet the metaverse, right? Because everybody looks a bit unrealistic, right? So now all the efforts that we do in our lab is starting from these representations, how we can find the garment deformations that would fit these particular humans, right? So so this concludes the first part of the talk. So now we know that we can represent humans using some representation that we more or less understand. And now the goal here is how we can enrich this low-level and coarse approximation, and how we can add clothing and perhaps appearance into these persons, right? That's where most of our research has gone in the last 2 to 5 years approximately. So first we're going to talk a bit about clothing. As I said, it's mostly work from ours. And actually, it's important to make a distinction here between reconstruction and animation, right? By reconstruction of clothing, I mean that I assume I have an image, and I want to extract the clothing that appears in this image, right? So this is useful for any 3D reconstruction task. And for animation, I mean that I have a naked human, maybe one of these SMPL body models, and I want to put digital clothes into this model, maybe to see how a garment would fit into this body, or maybe for my video game or for visual effects, etc. So we wanna apply some clothing to these humans, and it's important to distinguish between two different applications, right? So I will try to give a summary of techniques that are useful for each approach. All right, so for reconstruction, here I put a pipeline, and now we'll talk a little bit about the different steps that we use in our pipeline. So basically, it's a pipeline on how we can extract the 3D garment that this character is wearing. Here, the coloring of the projector is a little bit unfortunate, but you should see that this there's a lot of wrinkles going on here. Just imagine that. I think then they have different representation, different examples that they're going to be more clear. Right? Here, so here I put a quick preview on sorry, apologize. Here I put a quick preview of the different steps that we use to extract the 3D garment of this human. And again, each of the steps is using machine learning. So one first step that you can use is using one of these human parsing, or sometimes called human segmentation or image segmentation, that basically those are neural networks that, given an image, it predicts a label per each pixel, right? So there's people who have trained these neural networks to actually predict a label that is associated with a type of apparel or garment that wears. So having an image where you appear, it gives you another image where each pixel has a label, right? So we use this technique to segment the image, and now we know which pixels I want to focus on. So in that particular case that I want to reconstruct the t-shirt, I want to focus on the pixels that are color purple, right? This, again, open source implementation that you can very quickly go into this code and run it in your machine. It's very fun to play with it. Okay, so now we have human parsing. So I know the pixels on this image that I should focus, and by now you're already an expert, and you know that given this image, I can also extract the 3D body pose of the human, right? Using the approach that I just described. So now we have an image, we have some segmentation of this image, and we have some sort of 3D information of what's going on in this image through the 3D body model. Another trick that we can do, there's a lot of tricks here. Another trick that we can do is use another neural network that is proposed by another group that is a set of methods that what it does is, given an image, it predicts, this might be a little bit tricky to imagine, given an image, it predicts the normal orientation of each pixel. That means that basically a normal orientation is the vector that points orthogonal to the surface. So basically, given an image, you get still an image. So this is not 3D. What you see here is not 3D. It's just a color per pixel that is colored as a function of the normal vector of this pixel, right? What this means is that it gives more or less an orientation of what's going on in the image. But again, there is no 3D. It's a 2D image where each pixel has a color, and this color has information about the surface of the pixel, but there is no 3D. Okay. So now, using these 3 different steps that were proposed by our groups, what we do to recover the 3D geometry of the t-shirt is, assuming I have a 3D model of a t-shirt, which is I put there in yellow, there I really have a 3D model. What I want to do is I want to deform this 3D model such that it fits to this normal orientation here. So basically what I do is I kind of move the triangles of my 3D model such that the orientation of each triangle fits into the coloring that is estimated from the other neural network. I know there's a lot going on here, but it's just a quick review, right? So after this step, I've managed to deform my 3D model such that it fits to the normals that are estimated. And then basically we have another final step where we do some fine refinement. But it's basically the same. It's basically the same thing, but optimizing some of the parameters. And then at the end, what you see in the end is really 3D. So it's a render of the 3D mesh that is deformed to fit to this original image. So if you think about here, what we did is we went from 2D to 3D. We went from an image that was captured with a cell phone into a full 3D representation of the garment. And actually, this method works pretty good. So these are a set of videos that actually these I recorded with my cell phone in my living room. So here you can see that in the original video, that was kind of a sports t-shirt. And using this method, we recovered the full 3D pose and shape of the avatar. But what is most importantly in this work is that we are able to recover the fine wrinkles of the image. So here, what I'm doing, using my normal cell phone, I'm able to recover the 3D surface of a geometry that deforms highly over time. Right? So you should pay attention to the to the fine details that are here. So this is really 3D geometry that is deforming. So we are going from 2D information to 3D information, just using input camera that is in our mobile phones. Here there is no depth sensor, no multi-camera, no nothing. It's just a normal capture that we can do. So here we're demonstrating that we are extracting information about the t-shirt, and we're able to recover the shape and pose of the underlying human, and also the deformation of what he's wearing, right? So this is a huge step towards digitizing humans, because most of the humans that you see in your video games are almost rigid. So when you play video games, you rarely see any 3D, any wrinkle like this. And all the wrinkles that you see are either pre-baked or faked with different tricks. Here what we see is like the real geometry recovered in 3D. And again, each of the steps was done using machine learning. All right, so now we saw how we can represent humans. We saw how, using this representation, we can put some clothing on top that comes from the real world, right? So now this was mostly what we call reconstruction. So now we will touch a little bit of the animation. So here the problem is going to be different. Here the problem is going to be, I have an animated human and I want to put clothing on top. It doesn't need to be, the clothing doesn't need to come from the real world. It could be clothing that I want to put to my video games or visual effects or stuff like that. Okay, so here the problem is how can we learn to deform garments or any 3D surface using machine learning? So to reformulate the problem here, now the problem is going to be that I assume I have a virtual human, right? So I assume I have some pose and shape of this human, right? And now I want to use some machine learning tricks to infer how the garment would fit to this human, right? So the problem is different to the reconstruction. Here there is no image, right? Here is just animation or synthesis, right? Both are needed in order to digitize humans. Okay, so the results of this are going to look like this. So just a little bit of a spoiler to keep you awake. So here what we see is a machine learning model that is able to predict fine wrinkles on these different bodies. Here what we should see is that this is the same model, so it's kind of the same t-shirt, like an S of this model, in 3 different subjects. So you should see different wrinkles, right? So you should see, because the same t-shirt fits different to different bodies. So here you should see that one of them is more exhibits different dynamics than others, right? This one is a little bit more loose, and the other one is a little bit more stick to the body, because the body is bigger, right? So basically, this is what we, in the community, we call virtual try-on, because this effectively, what it does is basically allows you to try virtual garments, right? If you know the beta parameters of your body, then with this machine learning approach, you can see how a certain t-shirt would fit to this body, okay? All right, so now we're gonna have a quick look on how we managed to train this with machine learning. This was actually a work that we published in 2019, and it was one of the first works to show that machine learning was also good for this kind of 3D tasks. All right, so the approach here, as usually, we have some data set processing because we need some data, and then you have some runtime pipeline where we do the inference. I'm gonna talk a little bit about both. So for dataset generation, which is usually what you need when you train a machine learning model, in this case, what we do is we generate a synthetic dataset. So what you see here, it's a bunch of t-shirts that are simulated on top of bodies. The trick here, I know I'm going very quick, but the trick here is that in order to generate these very nice renders, my computer took over a week. Right? So we use physics-based simulation, with a very costly technique. And with physics-based simulation, you can get very nice deformations on top of this body. Now, the problem is that this is very slow and costly. And with machine learning, we're going to speed up this process, right? So the first thing we did was running this. Whoever's a little bit familiar, you can use even Blender for stuff like that. Okay? So you can simulate with Blender. This is a little bit slow. And once it's simulated, you have a bunch of data. And the cool part here is that for each of these frames, I have the pose that the human was having in these frames, right? So I'm going to use this as a annotations for my machine learning. Okay. Okay. I'm going to jump a little bit deeper into the algorithm. So don't worry if you get lost. There's just only a couple of slides to do that. And this is probably too low level for people who are not familiar with animation in general. But let's give it a try. So the t-shirts that I get from my simulator or even from my reconstruction, they look like this. So they are deformed and they exhibit a particular pose, right? So the first trick that we do to train our machine learning regressor is, and again, I apologize because this might come a little bit out of the blue for you, but you have to believe me that the first thing that we have to do is kind of find a common representation for all the t-shirts that they have, okay? It's kind of a process that sometimes is called normalization. So for us, normalization in this kind of a t-shirt domain is bring the t-shirt into what we call t-pose. So what you see on the right is the t-shirt is the same deformed t-shirt, so it kept the wrinkles, but we removed the deformation due to the body pose. So we are kind of, sometimes it's called unposing, right? So I'm gonna do this for all my data set. So then my data set is gonna be a set of t-shirts. I see a lot of strange looking faces in the public, so don't worry if you get lost here, but basically we will have a data set of t-shirts in t-pose, but they all exhibit different wrinkles. Okay, and the goal of our machine learning is try to learn to represent and infer these wrinkles. Okay, so I have this data set. I put those in my normalized space, and then the goal of my machine learning, you always have to think about what is your neural network predicting. So the goal of my neural network is going to be as simple as inferring this delta, which in the end is just some displacements on top of this. So just a super high level explanation here. So this is a mesh. So we have triangles and vertices, and this is like my mesh undeformed, okay, with no deformation. I assume I have this because it's my model, and what I want to do is I want to my neural network to each of these points here, which is a 3D vertex, to deform it. Okay, that's what I want to do. And I want to do this as a function of the underlying pose. So when the pose of the human is I raise my hand, I want some wrinkles to appear here, which basically for the computer, for the representation that I use, is just a set of 3D offsets that I'm going to add to these vertices, which in the end is a vector of 3 points per vertex, right? So actually, I encode this in a matrix that I call capital delta, and this is exactly what I want my machine learning model to do. And this is what I'm going to do in this runtime pipeline. So my runtime pipeline will have, we split it in 2 blocks, but there is no good, it's not super relevant here. But then I have a machine learning pipeline that it gets a beta parameter. Now we all know that beta is the descriptor of our body shape. And the template of the mesh undeformed, right? And then this neural network regressor, which is that simple, like this in PyTorch is like 2 lines of code. I want this to deform this template such that it fits to this body. So basically it will shrink or enlarge the t-shirt. And then I have a second neural network here that as an input, it doesn't only get beta, but it also gets theta. Theta is the pose of the human. Right? So then this second neural network is going to deform this one, and it's going to add the wrinkles. Okay? I have some nice visualizations here to see what's going on. Don't worry, we don't get into more, lower detail. But basically what you see here is that our neural network kind of deforms the original template as a function of this body. This body changes along the video, and then the t-shirt also deforms. So basically this first network has learned to fit coarsely the t-shirt into this body. When the body is too thick, then the t-shirt gets enlarged. When the body is very slim, then the t-shirt gets loose, right? So this is our first network, and then the output of this, we feed it to a second neural network. Here the results are a bit cooler to see. And basically having the already roughly deformed t-shirt and getting as a function beta and theta, which is a descriptor of what this person is doing here, I want to infer the wrinkles that match this input pose. And because I'm working in this normalized space, the wrinkles are actually encoded in this funny looking t-shirt that you see here, which is the wrinkles encoded in in a T-pose, right? Why we do this? Because actually learning this in this space is a lot simpler than if this pose would have the articulation of the body. Okay, so as output of this network, we have a t-shirt in T-pose that has some wrinkles that match the input pose, right? And now because we are in animation pipeline, I know how to skin this mesh, which is basically bring it to the pose here. Like this mesh also has some skeleton inside, and then I know how to deform also the mesh such that it fits the body in the end. Okay, so basically with this method, we're showing that neural networks can also predict the highly nonlinear deformations that our clothing exhibits when we do different movements, right? Okay, so now you are experts also in machine learning, so you can understand what's going on here, right? What's going on here is a human body model that is parameterized by pose and shape, and then we use these numbers to feed them into a neural network, and the neural network predicts the offsets of the template t-shirt such that they fit the underlying body. So, which is basically a super simple example of what is called virtual try-on, and basically all the big brands now are trying to get, right? Because what you want is you want to go to Amazon or wherever, fit your body parameters and get the render of how the t-shirt fits your body, right? So that was actually one of the first methods, yeah, to show that this was possible. There's a ton of things that needs to be solved here before you see that on your phone. We can talk about that later. But for example, one of the problems is that soft tissue is not handled here yet. For example, so if parts of your body are more rigid than others, this is not implemented. The other limitation is that this only works for this t-shirt. So if you change me the t-shirt, I need to retrain the model, which is not good. And some other limitations. Okay. I got a bit lost of time. Now it's 1 o'clock, so we have 15 minutes left, roughly. Yeah. All right. So okay. So actually, this worked pretty nicely, and it got quite a lot of attention in the academic atmosphere around virtual humans, right? Now I'm very quickly jump into. I will uncover some of the problems that this problem had. That this project had, and I'll show you how we can solve them as well. So one of the problems that we had in this approach that I just described, which is summarized here. So first we had some data generation, which was this data set. Then we had this neural network that we trained, and then we have some results. That's a quick summary of what I just described, right? So ideally, in an ideal world, we don't want this. Like whenever somebody talks to you about machine learning, et cetera, you always have to think about what data was used to train the model, right? And whenever we talk about data, as we saw in the previous talk, it's always a bit tricky, right? You have to generate the data. Sometimes the data is private, et cetera. No, you have to store it somewhere. Someone is going to complain that you're storing stuff that you shouldn't, etc. So data is usually a problem, right? So with machine learning, you usually use data, but there's also methods that are able to learn without data, okay? And actually, that's the second project that we did last year. And basically, now I'm gonna super briefly describe how you can do this with no data. So basically, now we're gonna train a neural network to deform 3D garments with no garments examples, okay? Sounds a bit like black magic, but it's possible. So basically, the trick here with in this other work is that you see that we are missing all the data generation part. So instead of training the network using this data, now we're gonna train the network using physics, right? So the trick here, I think yeah, this physics. I skip all the physics slide because I knew it was already almost lunchtime. But you have to think about that in the physics world, we know how garments deform. We know about forces, energies, stretch, bending, etc., right? And actually, if you look into the physics literature, we know how clothing deforms. We know some properties that clothing needs to fulfill. For example, you cannot stretch a certain type of garments more than X value. When you stretch it in a certain way, it deforms in another way, etc., etc. So there's a lot of rules and knowledge that we already have from physics. So what we did in this project is we trained the neural network based on the rules of physics, not based on data, right? We teach the network, hey, I know that if you're deforming a garment, the deformed garment needs to fulfill this. For example, it cannot be, heavily deformed, right? Because there's some constraints in here, right? So, and then we found a way to formulate this as a penalty for our neural network. And this basically allows us to train a neural network that, without seeing any data, can learn to deform data. I know this is a bit tricky to understand, but basically just a super quick, high-level interaction. Here, now we have a neural network that gets a pose and a shape. This is some sort of architecture. It doesn't make, it's not the goal to understand what's going on here, but it's simple. And basically, this network predicts something, this n times 3. It predicts some values. And then these values, we add them into the template, as we were doing in the previous project, right? Now we add these values, and then you see that now they show deformed. And I know I'm out of the thing. So here we add this. Initially, we had some random values here. We get absolutely random values. We add these random values into a T-pose, and then we get some wrinkles. Well, initially you're gonna get rubbish. And then in the end, we have some terms that kind of see what's going on here, right? And then we make sure that what's going on there fulfills some constraints, okay? And then we train this over and over and over and over, and in the end, what happens is that this block here learns to predict values that are not rubbish, that actually produce nice wrinkles, because we have a good definition of wrinkles from the physics point of view. Right? So basically this was published last year, and it was the first method to learn to deform garments with no data. So here we have a neural network that has learned to deform these garments without data, and actually it works better with data. There's some justification for that. But all the wrinkles that you see here, the neural network has learned them to do automatically. Okay, and the trick here is, again, using physics. It's a way to deform. So we're using physics to deform how humans move, if you want. Okay, so we have some these runs at runtime. So in our demo, you can pick the body and the shape and the different garment, and then this will produce a nice deformations for all of them. Yeah, it's of course not at the stage of commercial product. It's of course worse than physics-based simulation, but it's still very important to realize that neural networks can learn to do this with no data. That's the big point here. Okay, just to finish, I said that we talk a little bit about human appearance. We are lately using a lot into human appearances because now we have humans, we have some wrinkles on what they wear, but there is no humans. There's a lot of works. We haven't really yet published anything, but I just wanted you to see this really cool work published last year at SIGGRAPH, where we are using these powerful neural networks that are able to synthesize images, to actually synthesize images of humans, right? All this DALI, diffusion, stable diffusion, blah, blah, blah. All these can also be done to synthesize humans, right? So this, again, this is not work done in our group, but we hope to incorporate all this to our avatars. So what is going on here is that you get a render of this SMPL body model, and then you describe the outfit that you want and how the outfit look. And then the neural network generates this. Okay, but the problem here is that this is a 2D image. This is not a 3D model with texture, right? But it still is quite interesting to see that with machine learning, nowadays we can synthesize image, and we hope to use all these powerful tools to add texture into our humans. Okay, I think I'm almost out of time. I wanted to talk a little bit about more stuff that I'm going to show very quickly, also related to humans. So another, humans and clothing. So another project that we recently concluded is another open problem with digitizing humans is not to infer only the geometry, but also to infer the properties of our textile. For example, what I'm wearing doesn't deform as well as another T-shirt that I have in my wardrobe, for example, right? So the properties of what we wear is also important. Not only the geometry, but the physical properties, because the physical properties kind of condition what the deformation. No? So in this In this other project, what we did is we trained a neural network in which, this is a bit hard to see here, but basically we trained a neural network that using 2 input images of a patch of of the fabric that I'm wearing. You should see 3 different fabrics, and they exhibit different wrinkles. So a thin cotton, a thin satin, and I think the rightmost is pana. I don't know the word in English, but a thick cotton fabric. Okay, so in here, what you should see is that these renders exhibit different wrinkles that depend on the underlying material, right? And our neural network, what it does, it takes 2 pictures, and from these pictures is able to infer the properties of the underlying fabric. And this is actually a super important problem in digitizing humans that is largely overlooked in the literature, because people are only looking at the if the 3D or the images look good, but you need a good estimation of what's going on in the underlying model. And just to wrap up some other cool projects that we did with with virtual humans that didn't fit here. For example, in here we use also machine learning for virtual humans to model the soft tissue deformation. Again, all the video games that you play, the humans are completely rigid. So even if you see very cool renders, those are as rigid as this table, right? So they're not deform. So in here we use machine learning to learn to deform these humans as a function of their shape and their motion. So you should see some funny effects in this video, right? This again, we train machine learning to do that. It's something you can do with physics, but it's super expensive. With machine learning, we can do this at 1,000 frames per second, roughly. And some other projects that we worked on also related with humans and machine learning. In this other project, what we do is we tackle the problem of interaction with virtual objects. So here you have a virtual hand that touches a virtual object. And what is really hard to get in this kind of projects is the deformation that the hand suffers due to contact, right? This is something that as a humans, we naturally assume. For example, when I touch an edge, or when I grab my phone, or when I touch anything, my fingers deform slightly, otherwise I wouldn't be able to grab this. So it's actually really hard to make computers to really reproduce the deformations that our hands suffer due to contact. And in this project, we coupled physics and machine learning, and then you should see that there's a semi-transparent cube here and a hand that's manipulating the cube. And you should see that the skin of the hand very softly deforms when it touches the edges of the cube. And all this is also predicted with a mixture of physics and machine learning. Okay, so this is almost the end of my talks. Most of the projects that we develop, we release data and models. So if you like to play with this stuff, you can go to my website, or you just Google this, you will find it quickly. And then you will usually have GitHub repositories that to get you started with this. Well, here I talk a lot about many projects that I probably did the least of work here. So all this is through PhD students and postdocs and researchers at our lab. So a big thank you to all of them. And basically, I think that concludes my talk. So I'm happy to take questions.
Okay, if you have some questions, we have like
Pueden ser en español también, o sea, las preguntas.
Tenemos un par de minutillos, si alguien quiere alguna pregunta.
So I have a question regarding because you're using like real life pictures to train the model. So your training set is coming from like different, of course, light conditions and different camera lenses with different focal lengths. But we know, for example, with different focal lengths, actually there's a bias, for shapes. Like for example, your face would actually look flatter when you're trying to use a wide angle lens. So how do you overcome that kind of bias caused by by the perspectives of the
I
camera.
understand. Yeah, well, the only algorithm that I talk that would suffer from that is the first one, because all the other algorithms are kind of animation algorithms. So the input for the many of the algorithms is actually, let me see if I can get this. So most of the input is always based on these two guys here, right? So the problem is that how do you extract this from images if those images have distortions? That's the question, right? Yeah, first, it's not part of my business because I assume this works. But of course, the algorithms that do that basically are trained with data that kind of prevents this biasing. For example, there's many ways you can do that. You can perturb the image, such that simulate, for example, I take a single image and I want to be robust to other distortions. So then I can take this image, or synthetically, I can manipulate the image instead of deforming as the different lenses would do. But yeah, it's actually a critical point for all the projects that do this estimation of human body shape. They need to be trained basically with a set of images that is sufficiently distinguished from one another, right? Otherwise, you suffer from bias. And actually, the bias from camera lenses, there's another question there, I think. The bias from camera lenses is the least important one. The most important these days are in the racial biases and ethic biases, right? Because there's many of these algorithms that the first version only work with white American male humans, for example, right? So that's a huge bias that the community that is dealing with extracting these parameters is working on. With most of our works, we assume that we have the parameterization of the underlying human, and we work towards, adding stuff on top of these humans.
Hello. I just want to ask, when you talk about that you didn't use data to train the model in the second version, I think.
Yeah, in this one.
Yeah. It wouldn't be, you could say it is a unsupervised machine learning model. You could say it like that, or because I see the name self-supervised, but it has a difference with unsupervised machine learning.
Well, that's a huge debate, right?
Well,
that's a huge debate. To me, it's self-supervised because it does use supervision in the sense that these two functions that in the end, I check their value, right? So I check the value. The only issue here is that the value is not checked against ground truth that somebody annotated, is checked against some rules that I created. And then the amount of values that I can check is infinite, because it's based on a rule, right? So I just quick query this rule, and that's my supervision. So it's supervised automatically in a way. That's for me, it's supervised. It's true that there's people that told me, it's funny because this question comes in all different flavors. I also have questions telling me that this is supervised because it's supervised with a rule. I'm like, okay, whatever, Right? So it's a good topic, yeah.
Thank you very much.
Vale, pues nada, no tenemos tiempo para más preguntas, chicos. Así que muchas gracias y un aplauso a Dan.